Hi, my name is Jacob Tan, and today I'm going to be teaching you about differential equations. What do rabbits, objects falling at terminal velocity, economic models, and algae in a pond all have in common? These dynamic processes can all be explained by a mathematical phenomenon called the differential equation. Pioneered by the work of famous mathematicians Isaac Newton and Gottfried Wilhelm Leibniz, these equations can take many forms. The Verhulst equation describes logistic growth in populations. Partial differential equations contain partial derivatives of multiple variables. And ordinary differential equations, our equation of choice, can describe everything from particle motion to simple harmonic motion. A differential equation is any equation that has a variable and its derivative, and tells us about the change in a variable, usually over time. However, oftentimes, these equations need to be solved in order to become useful for us. Let's take a look at an example. Let's use the example of an object falling at terminal velocity. The free body diagram is shown below, in addition to Newton's second law for the situation. We can replace acceleration with dv over dt, which is change in velocity over change in time. This gives us a differential equation. We have a variable and its derivative. Velocity is our variable, and dv over dt is our derivative. Now let's look into how we can actually solve this. We want to use a method called separation of variables, which the goal is to get the variable and its derivative on the same side of the equation. So let's distribute out dv and dt, and then manipulate our equation to get bv and dv on the same side. We'll move m over to the side of dt since that has no variable attached to it. Once we distribute our variables, our final equation will be 1 over m times dt is equal to 1 over mg minus bv times dv. The next step in solving our differential equation is to integrate both sides. For the left side of the equation, the integral of 1 over m with respect to dt is just t over m. But for the right side, we'll have to use u substitution. Let's set our u equal to mg minus bv and derive our u expression. After we derive our u expression and manipulate our variables, we'll get negative 1 over b times du is equal to dv. Then we can plug our negative 1 over b times du in for our dv in our equation, giving us negative 1 over b times the integral of 1 over u du. The integral of 1 over u is the ln of u, and let's not forget to add our plus c. Our final equation is t over m is equal to the ln of u divided by negative b plus c. Finally, for the last part of our differential equation, let's plug our u back into the expression that we found in part 2. Now, let's move our c over to the other side for a reason that I'll explain in a second. Next, we're going to exponentiate both sides of our equation. And because of exponent rules, when we exponentiate c, we can actually multiply c times e to the negative bt over m equals mg minus bv. Now we can move our mg back over to the left side of the equation, and from here we're able to solve for v. However, we still have our c in our equation for velocity, which we don't want. And you might be tempted to stop here, but I'll explain to you why not. This equation for velocity, which we might know the shape of, we don't know the exact location of. This is because we don't have our c value. Our c value can shift our graph up or down, as you can see on the graph in the top right. So we have to use our initial conditions in order to solve for the specific solution, not the general solution. Since this object was dropped, we know that its velocity at time t equals 0 is 0 meters per second. Plugging 0 and 0 into our differential equation, we can find the value of c, which is going to be equal to mg. Then we can plug our mg back into our equation, and now our final equation will be velocity as a function of time, which will be equal to mg times e to the negative bt over m minus 1 divided by negative b. Differential equations allowed us to transform a static equation like Newton's second law and describe the motion of an object. Rates of change are all around us, which are all beautiful opportunities for differential equations. In addition, differential equations allow us to use slope fields like the two images below to visualize change in beautiful ways. I hope this video helped you appreciate differential equations, and thanks for listening.